Let's take a look at a new way of counting. If I have a bunch of people in a room and I want to know how many different ways I can line them up, or if I have decorations for a wall or pictures or something like that, how many different ways can I line those up? All of this has to do with counting and the different ways that we can count. The fancy words for those are permutations, and we're going to use factorials to do it. So this is lesson 1.6. If you're following along on our same textbook, it's section 4.6. Mr. Squirrel was wondering how many ways can the letter of the alphabet be arranged? That can get really complicated really fast when you think about the letters of the alphabet. So we've got, A, B, C, D, E, all the way down to the X, Y, Z at the end of the alphabet. And we know this to be true. So this is one methodology or one way that it can be arranged. But what if the B went first instead of the A? Oops, that's a D. And there we go. And all the way down to X, Y, Z. Again, okay, well, that's if the A is in the second location, but what if the A is in the third location and just trickles down and trickles down and trickles down and trickles down? So how many different locations can the A be in? Well, the A can be in 26 different locations, all the way down to the scenario where the A is actually at the end of the alphabet. So all the way down to where we get X, Y, Z, A. There's 26 spots or locations for the A. But then that means there's also 26 locations for the B, and 26 locations for the C, and 26 locations for the D and the E. That is a lot of different ways that we can write the letters of the alphabet, and that's called a permutation. All of those are called different permutations, and you can permute information, rearrange them around. So there's a great video on YouTube here, a TED Talk, on how many ways you can rearrange a deck of cards. And it's amazing, the number. So if you get a chance, please watch that video. It really explains it really, really, really well. Okay, so let's talk about factorials first. All right, factorial is just a way to multiply consecutive numbers. When we deal with natural numbers, so no negatives, no decimals, just whole numbers, how can we multiply consecutive values? And just for example, if I was to multiply 4 times 3 times 2 times 1, that's the 4 factorial. It's got an exclamation mark on it because factorials are so amazing. Now, why would we ever do this? Why would we do 4 times 3 times 2 times 1? Well, it's very similar to the alphabet scenario. In the alphabet scenario, I was doing 26 letters. That's a little bit crazy. What if we just did 4 letters? So A, B, C, and D. Well, the A can move around just like it did before. What we end up with, in fact, is 24 different ways. I'm not going to write them all out, but 24 different ways that that A can move around. So there's 4 ways for the A to move around. And if we just sort of focus on the A, okay, so if we pick A for the first location, how many different locations are there for the rest of them around? Well, there's 3 locations for the B. And if I put the B here, now there's 2 locations left for the C and the D. And you can use a tree diagram if you want to. So I could say, okay, I've picked A for the first location. What are the different options as I go here for B, C, and D? And so there's B, C, or D for the second letter. And of course, it might not have been the A, it might have been the B that was the first letter. And so then that means there's 3 different options, A, C, and D, and so on. And so it creates this really crazy amount pretty quickly. Whoops. Pretty fast. So the math for that is 4 options for the first letter, A, B, C, or D. Then there's 3 options for the second letter, and then there's 2 options for the third letter. And then once you've picked the first 3 letters, by process of elimination, there's only 1 location left for that last letter. We're going to see more and more examples of this. So if that particular example didn't make any sense because I went too fast, then just hold on. Now, of course, because this is a video, you can pause it at any time, slow it down, speed it up, skip ahead, do what you got to do as you watch this video. So factorials get really big really quickly. It's incredible. Like 4 factorial is 25. Well, 7 factorial is over 5,000. And 9 factorial is over 360,000. And we don't tend to think of it that way because it's just 9 times 8 times 7 times 6. We don't really think, oh my, it's going to grow so big. But it is. It's almost exponential. All right, so factorials do follow BEDMAS, though, and there are ways to simplify factorial scenarios. And there's always the when am I ever going to use this question. If you just hold on for a minute, you'll find out when this does get used if you just let me get past these. So if we had 8 factorial divided by 6 factorial for some reason, okay? We've got 8 items and we want to shift them around, and then there's some reason why we would be dividing out the 6 factorial. If we were to actually write that in expanded form, we would write it like this. Pretty gross. But now that we know what a factorial is, 8 factorial is this top part in the numerator, and 6 factorial is this denominator right here. But we also know basic math and multiplication, and the fact that 6 divided by 6 is 1, and this can simplify. So if 6 divided by 6 is 1, so is 5 divided by 5, and 4 divided by 4, etc. And so all of those different parts of this multiplication or fraction cancel out, which is a really bad way of saying it. They divide to 1. There's no actual canceling here. Nothing got destroyed. And that leaves me with 8 times 7, and 8 times 7 is 56. So it's a much smaller number, much easier way to do this. It's more palatable, if you will. Okay, well, what about 9 factorial divided by 6 factorial times 3 factorial? Well, we're not going to expand out the 6 factorial times 3 factorial. That's going to make things bigger. I don't want to make things bigger. I want to make them smaller. Well, if we take a look at just the 9 factorial, just for, focusing in on things. 9 factorial, or any factorial really, can be written as a piece of a factorial. So, you know what, let me go back to this canvas here. If I had 7 factorial, I could say that that's 7 times 6 factorial. And in fact, not only is it 7 times 6 factorial, it's 7 times 6 times 5 factorial. Or if I really wanted to, I could say it's 7 times 6 times 5 times 4 factorial. The factorial is just a way of writing out the multiplication in a condensed format. We assume that if we see 4 factorial, it's really 4 times 3 times 2 times 1. We're just not writing out the whole thing. And so my numerator could be 9 times 8 times 7, and then let's just get lazy and say the rest of it's 6 factorial. Now, why are you doing that, Mr. Brash? Well, I'm doing it because I've got a 6 factorial in the denominator. I'm being really smart about it. I didn't pick 6 factorial just at random. And so the 6 factorials can cancel, just like any other numbers can cancel. Because 6 factorial, 6 by 4, 3, 2, 1, and 6 factorial in the denominator, 6 by 4, 3, 2, 1. So I'm left with a 3 factorial in the denominator, which 3 factorial is just 3 times 2 times 1, which is 6. So 9 times 8 times 7 is my numerator now because the 6 factorial reduced to 1. And my denominator is 6 because 3 factorial is 6. So 9 times 8 times 7 divided by 6 is 84. You can just use your calculator to do that. We can do this with any number. As a matter of fact, it doesn't have to be numbers. It can just be algebraic statements. 9 factorial is a almost tangible discrete value. But what if we don't know what the factorial is? So let's just take a look at this n factorial. N factorial can be written, n times something lower than n times something even lower than that times something even lower than that. So what you're about to see looks a little bit crazy, but it's n times n minus 1, so like 9 and then 8. And then n minus 2, well, 9 take away 2 is 7. And it keeps going down until we get to 1. And the denominator, it started at n minus 1 just because that's what they gave us as a question. So the next one down would be like saying n minus 1, which is just n minus 2. And that goes all the way down to 1 as well. Well, we know how to cancel items, or at least to divide items so that they'd reduce to 1. And it just so happens like if I start at the right-hand side, 1 divided by 1 is 1, 2 divided by 2 is 1. N minus 2 divided by n minus 2, they're the same thing, so that reduces to 1. So all of that junk cancels out or reduces to 1. And that means I'm left with n. It's the only thing left. That's so we can reduce these factorials, do math on these factorials, combine them, add them, subtract them, all of those sorts of things. Okay, so factorials, great. So what? Why are we doing this? What's with the factorial stuff? Rearranging 4 people is a fairly simple thing to do mathematically, and I showed you with the ABCD, and so there's 24 ways to do that. We used factorials to get it. But what if we wanted to select and rearrange a certain number of people out of a group? So in the first example, I rearranged 4 items from 4 items. But what if I wanted to rearrange only 3 items from those 4 items? Or let's go bigger. What if I wanted to arrange 4 random people, random items, out of a group of 30? I've got 30 people in a class, students, gymnasium class or something like that. I need to pick 4 for a particular job, and it doesn't really matter who gets what job. The order doesn't necessarily have to be a specific order. And so there's lots of different ways that I can do that. First of all, there's the 4 people that I can pick, and there's lots and lots of options for those 4 people that I can pick. In fact, there's 30 of them. And then not only that, the rearrangement of those 4 people can be different. I might pick one person first, or I might pick that same person fourth. And there's lots of different ways to do that. So permutations are this arrangement of a subset of distinct objects. So a subset just being a smaller group. So if my set is 30 students, then a subset might be 4 or whatever size subset I decide to pick. So if a few items are selected from the sample, there's a denotion for it. It's denoted like this: P of n comma r. And because functions already exist with a P, like the probability, like P of something happening, we tend to write it like this, NPR. And I've actually seen it written a couple different ways. So instead of NPR, sometimes you'll see it NP with the R below the N. It really just depends on who's writing it, from what country did they come, and all of this other stuff. So just be aware that if you see anything with these 3 letters, it's a permutation of N and R. And then of course the question is, what the heck are N and R? Well, it looks like this, and the N is the total number of people, or total number of items, I should say, in the set. So it's the 30 in my example here. So N is the total number of elements. R is how many we have selected to rearrange. And don't worry yourself too much with why this is the equation. It is this equation. And if you wanted to look it up, there are lots of explanations out there as to why this is the way that it is. But what you're going to do is you're going to take your 30 people, and you'll divide by 30, take away the 4 that you're selecting from the group, and we permute. We actually use the factorial, I should say, to figure that out. So as an example, a permutation of 30 people pick 4 is 30 factorial divided by 26 factorial. And because we know how to simplify factorials, we could do that on paper if we wanted to, but there's also a button on your calculator. So you should find the button on your calculator that says NPR. Sometimes it's directly on the calculator by using a second function. So look for it in a different color, whether that's orange or green or whatever for your calculator. But if you don't have that on your calculator, look for a button that says PRB. PRB would be your probability section of your calculator, and you'll find your factorial button under there. I didn't mention the factorial button. I forgot to mention that. There should be a button on your calculator for factorials to do it for you. And there's the NPR button as well. So look for that on your calculator, says Mr. Squirrel. Okay, let's take a look at a couple examples. Oh, I've got a rogue arrow there. Well, we'll just ignore that for now. So how many ways can we arrange 7 students? How many, it's just a straight 7 kids, not from a large group, nothing like that. I have 7 kids, I want to know how many I can rearrange them. Well, we already know how to do 4 letters or students or things. It was 4 factorial, and so 7 is no difference. It's just 7 factorial. And again, do this on your calculator, look for your factorial button. It will have X exclamation mark or N exclamation mark or something along those lines, and it could be under your PRB function, depending on your calculator. Now this could also be written as the permutation of 7 things 7 ways. That's kind of hard to understand or explain, but if in my example before it was 30 items or 30 people, arrange 4 of them. Well, if this is 7 items, arrange 7 of them, we get this. And that doesn't really make much sense mathematically, right? Division by 0 is a math error. So if I take 7 minus 7 and I try to do factorial on it, in fact, 0 factorial is 1. Now, if you want to know why 0 factorial is 1, there's a great TED Talk video, or actually, it's not a TED Talk video, it's a number file video on YouTube. There's lots of these videos that explain why 0 factorial is 1. But I want you to think of it this way. How many ways can you arrange nothing? There's only one way to arrange nothing, and it's just to not have anything. You can't arrange it. It's just not there. So you can have one thing one way, but you can also have no things one way just by not having them. And so that's why it is what it is. But there's some really good math speak out there as to why that is the way that it is. Okay, so let's say we have 12 people at a party. And it's a little bit of a mature party. We're going to give people jobs. We're not just going to hang out. We're going to have some people prepare the food. One person prepare the food. One person serve the food. One person clear the table, and another person does the washing. And so maybe this is something we get together with our friends, and we just pick from a hat as to who gets which job. And so it's completely random. Not only are the jobs random and how they're assigned, but the people who get the jobs are random. So 8 of those people won't have a job this time, but maybe the next time we get together, we swap it out. Now, how many different ways can we do that? Well, if there's 12 people and we're going to pick 4 for a job, we might say it's 12p4, a permutation of 12, choosing 4. And I got to be careful when I say choosing, but you'll learn that in another video. Now, if we just simplify that using factorials, it's actually only just 12 times 11 times 10 times 9. As a matter of fact, if you don't even want to think of it using factorials, you could say, well, there's 12 people for the first job, whatever that job happens to be. Let's just pick one at random. And then that means that there's only 11 people left for the second job, 10 people left for the third, and 9 people left for the fourth, leaving the remainder, the 8 people, to do nothing and just hang out. So there's 11,880 ways that can occur. So this is a really good time to practice. Find that button, your NPR button on your calculator, and see if you can get the same number here. Now I've got another example that I don't have the answer for in the slideshow. I want you to try it yourself, give it a pause. And how many ways do you think that you can select and arrange 4 letters from the word factor? So none of these letters repeat. We're just going to rearrange 4 of the letters. Maybe we're looking for other words that exist inside the word factor, or I don't know, something like that. Well, in fact, if you use your calculator, the function that you're going to do is the NPR, and so you'll do 6, because factor has 6 letters, P4, which, if we were to do this the long way, would be 6 factorial divided by 6 take away 4 factorial, which is 6 factorial divided by 2 factorial. 2 factorial is just 2. And so what we end up with is 6 times 5 times 4 times 3 times 1, because the 2's, the 2 would have been here and the 2 would have been in there, and they're going to reduce to 1. And so you would do that on your calculator and get your numeric value. And that's how many different ways that you can rearrange 4 of the letters in the word factor. And I'm not even going to give the answer. Be confident in what you're doing. All right, well, what if there's identical elements? I mean, in the previous word, the letters didn't repeat. Okay, what about the word aardvark? That's a lot of repetition in there. We got 3 A's, we got 2 R's. Well, let's move around some of the letters. I'm going to focus on the A's, and I'm going to move the A's around. We're just going to swap the A's around and write it out again. So swap some A's around, move some A's around, move some A's around. Did you see the A's move? I didn't either, because we can't. They're identical. So when we have identical, we actually assume that they're so identical, like they're not even colored differently or bolded differently or anything like that. And so that creates scenarios that are equal to each other. And so we don't want to count duplicates like that. We want to avoid counting duplicates like that. Otherwise, we'd have math that just goes on forever and ever, because I could just swap the A's back and forth, back and forth, back and forth, back and forth, and you would never be able to tell the difference between them. So what we're going to do is we're going to count how many duplicates or triplicates or quadruplicates we have, and we're going to divide those out because we don't want to talk about that. So we're going to divide out the ones that we don't like. There's 3 factorial ways to move the A's around. If I were to color them or denote them somehow with a number or something like that, there's 3 factorial ways that those can permute in every different combination of the letters. Similarly, there's 2 factorial ways to move the r's around. And so I don't want those. So what we're going to do is we're going to permute the 8 letters, and we're going to divide out the 3 factorial and the 2 factorial. If the letters were different colors, if we were able to differentiate between all of them, we would just say that the answer is 8 factorial because there are 8 letters. But in fact, I can't tell the difference. So I'm going to divide out the 3 factorial and divide out the 2 factorial. And that gives me a slightly smaller number, 3,360. If I didn't divide out those different permutations of the duplications, what would I end up with here? 8 factorial, 40,000. So that's a little bit crazy. Okay, so if we do have permutations with alike elements, we would calculate it like this. N factorial is the number of elements that we want to permute, and the A factorial, B factorial, C factorial, those are just the number of alike elements. And because we don't know how many we're going to have, we actually finish off the equation in the denominator with an ellipsis. Okay, so for example, if we were to determine the distinct number of arrangements of the letters in multiplicity, that's a complicated word, and there's actually a lot of repetition in there. All right, I'd like you to pause the video and try this for yourself before you get to the final answer. So the number of distinct arrangements of the letters requires us to know how many letters there are. Well, there's 12 letters in the word multiplicity. There are 2 L's, 2 T's, and 3 I's. So we are going to do 12 factorial because that's how many letters there are. There are 2 L's, so we divide that out. 2 T's, we divide that out, and 3 I's, we divide that out. And by the time we're done doing the math, and this is why you need to know where the factorial button is on your calculator, because you're not going to want to do this by hand, we get almost 20 million. So even after dividing out those duplicates, there's almost 20 million ways to write out the letters in that word and not have a repetitious item. Like if we were to actually just take a notebook and every day write out one possible combination of those letters, it would take almost 20 million days. So let's go back to that example of the party. If we had 12 people in 4 jobs, what's the probability? So when we did it originally, we just did it for how many different ways can we select those people. But if you're there, if you're at the party and your friends are there, and we want to know what the probability of you and your friends are going to be busy tonight doing the jobs instead of enjoying the party, we would do it like this. We would have to take the number of ways that you and 3 friends can be selected divided by all the different possibilities, because don't forget that's how probabilities work. We have the number of the set we're looking for divided by the number of the universe. And so there are 4 factorial ways that those jobs can be applied to you and your friends, or that you and your friends will be selected. Whether you're picked first and then, your friends are picked after you, or maybe you're picked second, or you're picked third, or you're picked fourth, and all of the different permutations. And then the denominator is what we discussed before. If there's 12 people and we're going to permute 4, that's our denominator. Now it looks like this mathematically, the 4 factorial in the numerator, and 12p4 is 12 factorial divided by 8 factorial for our denominator. But thankfully we have calculators, and so we're just going to let the calculator do the work for us. If we wanted to expand it out and not use the calculator, it would look like this. And so mathematically that's 1 in 495. So what that's basically saying is there's only one time out of 495 times that you and your 3 friends will be picked for those jobs. So you have a pretty good chance that you and your 3 friends won't get picked all at once. Looking at it another way, it's not going to be very likely that you'll be doing those jobs with your 3 specific friends. Maybe you and 2 of your friends, you and 1 of your friend, or just your 3 friends and not you, 2 of your friends and not you, 1 of your friend and not you, or none of you. Way more different ways that all of those can occur. And I recommend just using your calculator instead of trying to simplify this all out yourself. Okay, so we've got a recommended list of questions from our textbook to try out for factorials and permutations. This is 100% something that needs to be practiced. Do as many of the questions as you possibly can, hopefully all of them, and you know where to reach me and your classmates should you have any questions.